Merhabalar herkese.
Hi everyone. Here in the 52nd session, we'll talk about smart buildings. I'll talk about. My name is Beril. I'm an architect, and I have a master's degree in the engineering. And I'll talk about sustainable and smart cities, especially working on the positive energy areas. And regarding that, the building systems are very important. And as we haven't said, the building systems consume 75% of the world, and 80% of the energy is responsible for 75% of the greenhouse gas emissions. And of course, the urban structures is almost 30%. So in the energy transformation, it is very important. And of course, with the district approaches, there will be more energy efficient, less energy consuming buildings should be there. And it is a very session. We'll talk about the digital building systems.
First, I would like to present the presenters. Professor Agis Papadopoulos is from the Aristotle University of Thessaloniki, and he's also visiting professor at the Technical University of Hamburg. He's a mechanical engineer, but also specialized in energy conservation and environment and solar thermal systems as well. He's teaching energy conservation and renewable energy resources, energy and environmental design of buildings, economics and policies. İkinci konuşmacımız bugün Altug Karatas olacak. Kendisi Vatan Enerji Hizmetleri'nde
speaker is Altug Karatas. She is working in water energy systems. He's a graduate of Yıldız Technical University, mechanical engineers, and he had MBA in Yıldız Technical University at the pressurized air systems, high efficiency cooling group, and the cogeneration projects he's been working here.
She's an artificial intelligence leader at Honeywell, and also driving the AI for smart buildings, automation, predictive maintenance, and optimization of operations. And in the past, she was also involved in renewable energy, automotive, manufacturing, real estate, and healthcare projects as well. Ve son konuşmacımız da Onur Enerji'den Sayın Onur Günduru.
The last speaker is from Onur Enerji, General Director, and he's Boğaziçi University Energy. He has a master's degree in Boğaziçi University Energy Conservation since 2000. He's been working in energy studies and energy projects and verification. He completed more than 50 energies, and he is working as board of directors in CNN, and he has an investor in the low carbon energy projects. So I'd like to give the floor.
Professor will talk about potential in non-residential buildings, so-called tertiary, such as shopping malls, hospitals, educational and office buildings, for providing energy efficiency. And this energy efficiency results in reduced operational costs, increased well-being, and increased productivity of the staff as well. So what we may call as secondary benefits, let's say. And so he will also present some examples of refurbishment of the building envelope and advanced HVAC systems. So let's listen to his presentation on decarbonization strategies for resilient non-residential buildings. So Professor, the floor is yours. Thank you very much.
Yep, thank you very much for the very kind introduction. It is a pleasure and an honor to be having the chance to share a few thoughts with you at the Zero Build 21 conference in Turkey. And now if I manage to share my screen, yes, I think it should be working. Very good. So the idea is that I would like to share with you some thoughts about how we are proceeding on two different tracks, which are sometimes considered to be opposite to each other, but I believe in reality we are moving in the same direction. In the last 2 years, due to the COVID pandemic, there was a lot of talk about the resilience of systems, the resilience of the healthcare, the resilience of the energy systems. But this has also been a lot the case due to the effects of climate crisis. We have seen the terrible fires in Turkey, in Greece, in Portugal, or the floods in Germany. So we have to approach buildings on the base of how they can anticipate, absorb, adapt, and eventually recover from disruptive events. Resilience is often considered to be some metaphysical topic between politics, economics, whatsoever. But at the end of the day, I believed strongly that this is an engineering problem.
Interrupt for a second.
Yes.
It's not full screen, so could you make it full screen, please?
I thought it would be.
Now,
I thought.
Now it is full screen. But can you change the slides?
Yes. Is it okay now?
No, we cannot. We just see the main slide, the title slide, but I don't know.
I changed the slides on my computer. Terribly sorry about that, but let me try again.
So please close the connection, and our team will share the screen for you. Okay? Is that okay?
Yes, that's fine with me. So what should I do? Yep.
Just stop sharing, and our team will help you.
Okay, that would be very kind.
Perfect.
Okay. So if we could have the next slide, please. Then, as I said, resilience is at the end of the day a problem of engineering. At the same time, sustainability is a term that has been in the focus of interest since the late 1980s, and it has been an established term. But we have realized that sustainability is a very generic term. In reality, we have to speak of decarbonization of our whole world if we want to move towards and achieve the goals by 2050 and hopefully achieve climate neutrality. As I said before, resilience and sustainability are sometimes wrongfully considered to be contradictory goals. A very easy example to understand is that when the COVID pandemic emerged, the first directive that was issued from ASHRAE and the other organizations working in the field of indoor air quality was to increase fresh air supply to buildings to 100%, stop recycling air, which of course is not very good idea considering energy conservation and decarbonization, but it was deemed absolutely necessary to improve air quality. But as we shall hopefully see within the next few slides, there are ways to tackle those problems and to ensure both aspects, resilience and sustainability, at the same time. So if we could have the next slide, please. I'm sure that after 3 days in this very nice, very broad and very interesting conference, the figures are more or less known to everyone. But it's not bad to remind ourselves that despite the efforts of the last few decades, the energy demand is rapidly increasing all over the world. So in the next 20 years, it's expected to increase by almost 48 or 50%, despite using more renewables and less fossil fuels. Relatively, absolutely, the demand is increasing. And what is very important, it is increasing not in Europe, not in the North America, but it is increasing mainly in the expanding areas of the economy and the population in Asia and the Middle East, and it is also expected to increase in Africa. And this increase at the pace at which we are moving cannot be covered fast enough by renewables. So we have to utilize energy conservation and rational use of energy methods. So if we could have the next slide, please, then we could see that commercial buildings are some of the most important happy energy eaters. In the United States, they account for roughly 20% of electricity demand and energy demand. In Europe, Australia, and the tigers of Asia, of Singapore and Hong Kong, up to 10 to 12%. And even in other countries, they are no less than 5 or 6%. Expressed in terms of specific energy consumption, a typical mall in Europe consumes about 500 kilowatt hours per square meter, which is a lot of energy. In the States, it's more than 600. In Hong Kong, it's close to 800. So it's huge amounts of energy that are used to provide thermal comfort and indoor air quality and lighting in those temples of consumerism that halls are. If we can see the next slide, then we could also see that hospitals, which have been proven to be one of the most crucial link in the health system in the last 1.5 years, are also extremely important energy consumers. An interesting study carried out by some Spanish colleagues a couple of years ago indicated that hospitals in Europe consume on average anything between 400 and 1,000 kilowatt hours per square meter a year annually. with a very broad deviation that depends on the hospital type, that depends on the services it provides, and that depends obviously on the age and the systems of the building, but these are huge amounts of energy. And as you can see on the right picture of the slide, even if you compare a same size hospital in Norway and in Greece with the extremely different climate condition, the causes of consumption do not differ that drastically. You need heating, you need cooling, you need lighting, and you need provision of electricity to the vital systems that provide the healthcare. So before we spend too much time thinking of how we can improve the energy efficiency of residential buildings, which I do not want to downplay by no means, since they are 80% of our building stock, if we want to achieve our energy goals for 2030 and 2050, we have to move fast. And experience has shown that it makes much more sense to focus initially on the big energy consumers, where you can achieve economies of scale and scope, and move then towards the smaller buildings, which as a rule are the residential ones. If we could have the next slide, please, then we would see that, I think this should be fairly known to all of us who are working on the field. If we want to decarbonize a building, an industrial process, whatever, there is a very straightforward strategy. We have to understand the problem. We have to reduce the requirements in the case of buildings, heating and cooling, i.e. we have to make a better building envelope. And I have seen in the program that there have been the last few days of some very interesting presentations on that. Then we should proceed with having an efficient heating, ventilation, air conditioning system, whatever this may mean. I mean, the efficient and whatever the system may be. Then we should try to reduce the electrical requirements that are linked to lighting, plug loads, and all those small causes of consumption, which at the first glance appear not to be that significant, but in reality are very important players. And only then does it make sense to utilize renewable energy sources, because it doesn't really make sense to start by utilizing renewables in a building that is uninsulated, that has an inefficient chiller, and where lighting is still dated back to the 1980s. How can we proceed to implement the strategy? Thank you. There are many tools, and thanks to the technological developments, and I'm sure also in this session there will be some very interesting points of reference on these, we have many tools in our basket. If we want to improve the energy efficiency of the building envelope, we have excellent thermal insulation materials. We even have super insulating materials. We have cool materials that help us reducing the cooling loads. We have smart glazings, which especially in office buildings play an important role. So there's many things, there are many things that we can utilize. Considering heating, ventilation, air conditioning, if I remember what the efficiency values were when I was a young student 30 years ago, 35 years ago, we have trebled the efficiency of heat pumps. We have increased the efficiency of boilers by 20 percentual units. We have high efficiency combined heat and power. And of course, we have all the peripheral systems needed to make HVAC run feasibly. Probably the single most important advance in the tools that we have will be discussed by the following speakers, has to do with building automation controls. The advance in IT, the advance in artificial intelligence, the advance in sensoring has given us unique opportunities to have very flexible and very reliable operation of the HVAC systems that run in an energy efficient building. And of course, if it comes to renewables, if you just think how much more expensive and how less efficient photovoltaics, solar thermal systems, or heat pumps were a decade ago, not a century, then one can realize that the progress is immense. Finally, a very separate sector over the last decade, perhaps, has been the one of the facades. You can call them smart, you can call them adaptive. We design facades as integrated systems of a building that can cover at the same time in an efficient way with lighting, ventilation, waste heat recovery that respond to the demand. And there are many more, of course, which we could discuss if we had 2 hours time for a lecture. We don't, so we proceed with a couple of examples. We have excellent thermal insulation materials that can be retrofitted in buildings and that can achieve U values of below 0.03 watts per meter in Kelvin. At the same time, a factor that has been often overlooked, those materials are today much more environmental friendly because we don't use any more hydrocarbons for their production. They are much more safe because they are resistant to fire, and they are also cheaper per unit of energy that they can help reducing the transmission. So there is a plethora of materials which can be used for the various building elements in the building envelope, and we can insulate and reduce transmissivity losses, which still are more than 30 or 40% of a building's losses. If we see the next slide, then we can see that perhaps the most important progress over the last 15 years has been in the use of cool materials. In materials which can be paints, foams, tiles, that have a very high solar reflectance in the thermal spectrum of the radiation, and which can reduce surface temperatures by anything between 20 or 40 degrees, and hence reduce the temperatures in the floor beneath the roof by, let's say, 3, 4, 5 degrees Celsius, which makes a lot on the cooling load. What is more interesting is that you can use these materials, which, as you can see in the picture, can be sprayed fairly easily, to cover, for example, the air ducts of the HVAC equipment on the roof, where you have the very first, very expensive part of losses, since you have nicely conditioned air being exposed to the warm Turkish or Greek sun, and this is not necessarily a recipe for high energy efficiency. On the next slide, we can see that glazings, which are still the Achilles reverse in terms of solar loads, have some also very remarkable steps of progress. Low emissivity glazings, which reduce thermal transmissivity, are well established, and they have become also quite cheap over the years. 10 years ago, they were 50% more expensive than conventional glazings. Now they are perhaps 10 or 15%, and they reduce, depending on how you place them, cooling loads in the south of the world or heating loads in the north of the world considerably. But what is more fascinating in reality are the new generations of intelligent glazings. You have electrochromic glazings, which are already also in the market and quite successful, which reduce depending on the, photochromic glazings, which reduce depending on the intensity of solar radiation, the translusivity, and hence you have smaller cooling loads when the sun is shining bright, and they get again more transparent when the sun goes towards the sunset. And you have, of course, also the active glazings, electrochromic glazings, where you can control yourself how much light you would like to have come through your glass, and in that way also how much cooling you can have, or how many solar loads you can have in the building, and respectively adapt the function of your cooling system. And if we see the next slide, then we will see that there are many ways in which we can utilize those tools, also linked with renewable energies. This is a building that's already 15 years ago, almost 14 years ago, when it was constructed in Athens. The lab I have the honor to chair was actively involved in its design. It has been based on retrofitting an existing building envelope. It was not yet equipped with HVAC and other mechanical systems. And it's an office building that is packed full with renewable systems, flat plate solar collectors, Fresnel concentrating collectors. It has a geothermal heat exchanger below the building, and those systems together feed an absorption chiller that provides 65 kilowatts of cooling. You have also some photovoltaics. These are on the left side of the facade, where you can see the image of Prometheus, who brought fire to the human beings. And you have a big concrete tank beneath the building, where you can store the surplus heat so that you can utilize it, let's say, after it can cover a demand of, let's say, about a week. Overall, it is a building that has a renewable fraction of about 67%. It can have an autonomy, which is a true essence of resilience, of, let's say, 5 to 7 days. And it was a building that was finished with using market available materials, hence for its day, it was state of the art, but it was not out of this world. Now, what's more important, perhaps, it's been operating now for the last 14 years, and it has proven to be also reliable and without major problems in this otherwise fairly complex set of energy systems. The question that arises is such a building enough? And if we shall see the next slide, then we can answer that it is good, but it is not good enough. Because as we find out, we have to think more towards resilience. And by resilience, we understand the potential of a building to reply to possible threats to the power supply. Now, one always has to weigh the impact versus the likelihood. It's not very likely that you have a pandemic. It happens perhaps every century. But when it happens, it has a tremendous impact on the way in which our buildings have to perform, especially the non-residential ones. On the other hand, it becomes more and more likely that you have heat waves. And I think everyone who lives in the Mediterranean has quite an experience on that. The impact of the heat wave is not as dramatic, but it is still important. And this shows us how we have to plan our buildings. So if we could see the next slide, then we would see that if we define resilience as the system's ability to anticipate, absorb, adapt, and recover rapidly from a disruptive event, then it becomes clear that the building has to be able to survive, let's say, a cut in power supply because the wildfires have interrupted power transmission or because the snowfalls have led to the same event. That has to be able to withstand 5 days of extreme heat when its HVAC system is working overtimes. And this has to be done in a way which is different than what we used to do in the past. In the past, we used to say, okay, let's double the capacity of the system. We have 2 chillers instead of 1, we have 2 boilers instead of 1, and so we shall be happy to survive. This may be resilient, but of course it's not sustainable. So if we could have the next slide, please, then we would see that the paths towards resilience are based on 5 approaches. A, reduce, shift, and manage load. I think there's a very interesting presentation on this after a while. B, generate energy or power locally. Combined heat and power and renewable, if smartly used with microgrids and storage, can cover the base loads even of hospitals, let's say 40, 50, 60% of a hospital's loads, so that they can run the building even in cases of crisis. Of course, in order to make this work, we need a highly advanced automation and control system. And this has a lot to do not only with the hardware, let's say the building automation and control system according to EN 15232, but also with the software, which allows a very smooth integration of all those aspects. This is obviously linked with the controls, which are becoming smarter and smarter. And eventually this is linked in how we integrate, let's say, the building with the grid and possibly or probably in the near future with microgrids with other buildings. In the next slide, we can see that in order that this is successful, we have to keep in mind the technical dimension. We cannot simply add renewable CHP or even a microgrid to a building if the heating and cooling and hot water provision systems are not thought to operate as one. So we can have an electrical system, electrically driven system. Let's say you have a big PV, or you have this electricity from the CHP that drives an electrically driven a conditioning system and hot water supply, and this can run well. But if you have a traditional heating system with a boiler, then you can see how this can be most suitably adapted to work hand in hand with the various renewables. And everything that we do in that aspect has to be adapted to the building envelope so that you utilize thermal storage, insulation, shading, and the facades and things like that. So it is the technical dimension is in reality a question of very well-planned and well-executed integration. On the next slide, we can see that this is there's a lot to do with how we manage the demand. Traditionally, you can do 3 things: shift the load, for example, by using ice storage so that you can capitalize on the availability of electricity overnight so that you can store heat and use it for your air conditioning system over day. Shave the load by reducing solar loads and hence air conditioning by having a nice sun protection system or some advanced glazings, or fill the valleys so that you have a more uniform valley consumption profile, demand profile, where the utilization, let's say, of a CHP, of a combined heat and power system, makes much more sense. But this is not a trilemma. In reality, we have to do a bit of everything, because you can't simply solve all your problems, let's say, by shaving the loads. Then you will have a building that is not functional and safe. So if we see the next slide, please, then we can see that the main step ahead, after having done a building that is sound and well and effective and resilient, is integrating it with other buildings, integrating sort of a local microgrid, integrating it with the electricity and gas infrastructure. And especially as we are moving towards also a horizontal integration of systems, this becomes more and more important. One has only to think of reducing the impact of transport, which leads to electrical mobility, to e-vehicles. If you have 20 or 30% of your vehicles fleet being electric, and you haven't planned your built environment so as to support them in an efficient and effective way, then you will end up probably in a mess. So we don't simply have to dimension renewable systems on the buildings with respect to the peak demand of the building itself, but we have also to keep in mind that buildings will be able probably to support the vehicular fleet of the hospital or the school or the university in order to reach an overall optimum result. If we have the next slide, please, and I think I'm slowly coming. One example. This is a big hospital in Alexandroupolis, very close to the Turkish border. Constructed back in the late 1996, if I remember correctly. It's a quite big hospital, 88,000 square meters of air-conditioned area, 670 beds, that has an average consumption of about 420 kilowatt hours per square meter. For a hospital, it's a decent consumption. Still, a couple of years ago, we did a study that is hopefully being implemented in 2022, that if we utilize, let's say, a very straightforward CHP plant with two units of 1,750 kilowatt each, they can run at a base load of 4,500 hours annually, which is fairly reasonable. They will be able to cope 70% of the requirements. Doesn't make sense to go for 100% feasibly, it's a disaster. And we can achieve primary energy savings due to the much better efficiency of combined heat and power of something like 16%. It may not sound a lot, but if you think what 16% in the hospital sector would mean, which is a big energy consumer, then it's a very, very important step towards reducing carbon emissions from buildings.
Professor,
I have two slides.
Yeah.
Okay.
You're already
so,
over time.
Sorry. And this can be done at a payback period of 5 years. If we see the next slide, please, then this is only a reminder that whatever we do, high-end ambitious strategies, IT, CHP, PVs, whatever, this is important to happen on the base of an integrated assessment of the energy renovation measures, from the plain simple facts, insulation, to high-end IT. So if we come to the next slide, which is probably the one before, I hope I have convinced you that resilience and sustainability are in reality not contradictory terms or goals. If we make our buildings more sustainable in this advanced way, then they become automatically more resilient to extreme problems and phenomena. Hence, and I come to my last slide, the goal should be to promote resilience, to promote decarbonization, and not to forget to promote also the social integration factor, since buildings have to be affordable by those who construct them, those who run them, and those who use them. Thank you very much. I hope I didn't take too much of the extra time you were kind enough to give me. Thank you.
No. Thank you, Professor, for the very well organized presentation. And I see that the tools listed for effective decarbonization strategy is the key to start. But I think, of course, especially these new innovative digital tools play a key role as well. But towards resilience, resilience decarbonization, more actions on sustainability should be taken, as also you have suggested so-called electrification of systems as well. So thank you very much for your presentation.
Thank you.
Şimdi ikinci konuşmacımız Altug Bey'e geçelim. Altug
Now, let's move to Altug Bey. He is the second presenter. He will make a presentation on digitalization in energy, because digitalization is very important. And from one point to other, it's important for us, and we can consume less energy while we work more. And there is a slogan: control, monitor, control, and improve the energy. Hello, everyone. I would like to extend my greetings to all people from Turkey and from different parts of the world. Kahve is very important for us. And all colleagues who are interested in this zero energy, and hope that this event will make a tiny contribution to the energy saving and to the energy efficiency, which is very, very important for us. As you said, I have been working in this sector for more than 20 years, but I have been working in the energy efficiency for 16 years. And while we work on these studies, we save energy. And while we are trying to find solutions to achieve energy efficiency, we realize that digitalization is very important. That is my topic for today. And we can manage the system and we can save energy. I will share my screen. So if you want to share my screen, if you want to share my presentation, I'm ready. Or I can share this monitoring and management of the energy. Monitoring of energy was not an issue 5 years ago or 10 years ago. It was not an issue at all. There were some meters to control this issue. For example, we had these systems to heat waste systems, or we were trying to monitor everything, but the change is so fast, so rapid that it affects our life. For example, last year, online tools became so important for our life, especially online communication tools. And as a result, we developed a software to monitor the energy in an online way. And we aim to achieve energy efficiency in an online way through our software. Of course, there will be colleagues on the ground, on the field, and we need to get data. We need to process them, and we need to interpret these data. And we will have some projects so that we need to reduce CO2 emissions. This monitoring and management are important for us, and I will show you some examples. And if I have enough time, I will be happy to share everything. So what do we mean by energy efficiency, energy monitoring, energy management? Let me repeat the definition once again here. Energy efficiency means you can turn off one of the bulbs or lights, for example, and it may not be enough for your lighting, but you can still save something. But as for the energy efficiency, means you maintain, you keep the comfort in your life, or you do not reduce the quality in your production, in your manufacture, and on the contrary, you may improve the comfort, you may improve the standards, and then you still save energy. Of course, energy saving doesn't mean there is energy efficiency. That is our point. And as for the workplaces or institutions, the previous panelist, our dear professor, stated, there are hospitals, shopping malls, schools, etc. And we need to monitor and track the energy consumption in real time around the clock, every day. So we need to set up systems that enable us to monitor all these data in real time. And I will give you some examples. In next slide, you see that what do we have as for these monitoring solutions? It is an online around the clock monitoring system, and we also look at the consumption points and also our habits. And in these systems, we have some slides. There is also a need for alarming and also notifications, because people may not stand in front of the screens around the clock, even though the system monitors the consumption, the system around the clock. So there is need for warnings and also notifications. It is very important for real human beings, and also it is important for the electricity, for heating purposes, for cooling purposes, and also the real-time consumptions are very important. And also we need to know the CO2 emissions in real time. And we talked about the air conditioning, cooling, and heating purposes, and all these issues are important for us. And the applications that you have are very important in terms of getting detailed and accurate data about the efficiency, or if there is any problem with its efficiency, we need to know the gap so that we can work on it, we can fix on it. And this system should enable you to see all these details. And of course, it might be factories or it might be shopping malls. And there is an important point, and it is ERP integration. And as our dear Professor Aegis Papadopoulos stated, it is important for having all these details, and we need to know the energy concentration, and it needs to be integrated if there is a system, or the system itself needs to analyze and needs to monitor and calculate all these data and all these values. Of course, it is important. The technological infrastructure is very important, because all the systems can be efficient, even though they are working remotely. And I told you that I would give you some examples. For example, we have this observer energy monitoring and also management system. You can see the interface. There is a page for the manager, and you can see the graphs, or you can see the real-time consumption, even though the billing process is not completed. You can see the real-time consumption. So studying on this energy efficiency is still efficient, even though we work in a remote way. And we also see the energy efficiency in percentage and also in details. Moreover, we can also go into more details. For example, if we use an air conditioning and if we get 100% clean air, and now it is a common practice during the pandemic, especially in shopping malls, that it is important for health, of course. And then if you set up heat recovery system, you also get details about the efficiency resulting from the heat recovery system. And as a result of all these recommendations, I mean, the system makes certain recommendations, and then if you follow these recommendations, you need to know the outcomes, the achievements, and the savings or the efficiency level that we aim. So it is not only monitoring, but also management. So next slide, please. There might be several points. There might be hundreds or thousands of points that we need to monitor. And of course, there might be different parameters like temperature, pressure, or the level of cooling, the level of heating, or electricity, energy, the ladders or lighting. So there might be hundreds, even thousands of points to be monitored. And we still need parameters to see and to monitor the gaps. And even, as I said before, there is a feature of warning and notifications. And there might be some location-based analysis, for example, in a conference room, in a meeting room, or even a boiler. Even the chiller itself can be monitored and can be managed, and we can monitor its workload, its consumption trend, and its dense hours or rush hours, if we use the term to define its working hard, and what will be the savings, what is the potentiality here. So all these issues, all the energy points that generate power that can be monitored, and we can also get an idea about the billings. And it is not only the energy costs. Of course, energy costs are important, but it is not only the costs. We also need to think about the CO2, because it also costs something. And we need to work on all these issues, all the units, all the machines, all the meetings, all the meeting rooms, or all other offices can be monitored via this software, and we can get digital data. And these are the standard, these must be the standard features, and this is what we provide in our system, which we call monitoring or the observer energy system. And we can also make comparison, because we think that climate change is a fact. And so temperature may get cold, the weather may get cold or hot, or the temperature may decrease or increase. So this monitoring and the management system, we need to have certain maps. So it might be a weekly map, or it might be a monthly map. And you can see in square, on the right side, it is a circle. On the left side, it is in the form, it is a form of rectangulars, and we pay attention to the, for example, working hours, when they begin, when they leave the office, etc. So you can see all these details. There are different examples. I'm just trying to show you some more recent examples. So the energy density is very important. And it is important for us, the energy density. So we should not compare it on the basis of the bills, but on the basis of the energy density. And the energy density maps need to be created. And we need to focus on these concentrations so that we can achieve the energy savings. Let's continue. We need to have some alarms or notifications, as I said. For example, if we say it's the outside temperature, if there is a 7 Celsius degree difference between the outside and inside temperature, then we can get a notification, for example. For example, if it is 27, 28 Celsius degree, and if we make it 16 inside as a result of the air conditioning, it may not be so efficient. So if we put criteria, and if it is above or below this value, then we need to get an alarming system, because we need to set the limits. There must be certain alarms when it reaches the below or the above. And when there is this notification, it must act. Therefore, this digital energy monitoring and also management system, putting certain limits and also alarmings are important features. Next slide, please. Another important point, it is the most important point, is that the energy management system. To me, monitoring and also management system for energy, we have this module, and in Turkey, it has become to some extent an obligation, and in buildings and in private sector for industrial facilities, the energy management officer must work and must be recruited, and it is compulsory. It is compulsory, and it needs to be completed by 2023. And you need to manage your energy in a sustainable way. You need to control it, and you need to get results. We add this issue to our module, and we have all the systems. And of course, if you control all the energy values from the system, then this ISO 50001 is important. Next slide, please. And also, it makes certain recommendations. For example, in a municipality building, we worked, and as a result of our monitoring system, which we call it Observer Energy Management System, we have energy potentials in, for example, theater halls, that we created certain maps of energy density. And when we monitored that area at nighttime, we observed that there was a huge energy or dense energy entry and the output of these dense energy. And during the nighttime, in some departments, there were high consumption levels and amounts. And we always say, even it is in standby, that it consumes energy. And we can solve this issue with an automation system. That's what we recommended to the municipality. And we monitored and we interpret all this data, and we created a map of potential savings and energy savings, energy efficiency. These are the recommendations, and these theoretical data need to be applied in real life. And we also need to monitor this implementation phase so that we can see the efficiency of the CO2 emissions or how we prevent it. Of course, those who know the issue, let me repeat, those who do not know it. And there is this energy efficiency radio program that I have every day. As our dear professor, Mr. Papadopoulos, stated, there's a huge potentiality, and the natural gas bill, for example, might be double because of the inefficient energy buildings. Another point is that means, so if there's energy efficiency, then you can reduce your bills to half. So 1 Celsius degree means 7%, 5 to 7% energy consumption. So in cooling purposes of the AC, 1 Celsius degree, so if you cool it down in an unnecessary way, then you consume 6 to 7% electricity consumption. That means a lot. And of course, the automation systems can save a lot and can make contributions to the efficiency a lot. You can control it in an automated way, in a remote way, and you can make certain arrangements. And using this 100% clean air, it is important for us. Apologies. So we are running out of time. So can you wrap it up? It is same for the equipment. Let's skip this part. Water. In fact, Turkey suffers from drought, and it is a case in other countries as well. So we need to save water. Renewable energy, that is an issue that we have discussed. So there's a law that regulates up to 10 kilowatts. Yes, next slide. Automation. Automation. So monitoring is not enough, because in the past we were saying monitoring was satisfactory and was efficient, but monitoring is not enough. We need management. We need for management, and so there is a there is need for a central management, or also automation systems can save energy and can make contributions to the efficiency. And then we can achieve zero build, which is the title of this conference. And this is the last slide. Let me share some percentages. It might be up to 30% in heating and lighting with appropriate lighting and also sunlights. We can save energy up to 45%. And if we pay attention to this issue, we can achieve it. So these are my contact details. Thanks a lot for your patience. Everyone must take responsibilities and fulfill their responsibilities to achieve this, the reduction of the CO2 emissions. So to me, there must be a course in our national curriculum in all levels, primary schools, secondary schools, etc. Thanks a lot for your presentation. I fully agree with you, because these systems need to be integrated into automation so that we can achieve it. So you showed so many cases, and you also shared some figures with us. And you also talked about how we can achieve efficiency. It is very important for us, and it is quite informative.
As a technology enabler for bringing about building energy efficiency in buildings. So let's listen to her presentation on data intelligence for smart buildings. Ms. Sandeep, the floor is yours. Thank you. Ms. Sandeep, we cannot hear you. I don't know if you have started talking.
Am I audible now?
Now we can hear you. Yeah.
Thank you. Yeah, let me share my screen. Please let me know when it's visible.
It is already shared, I think, by the organization team. So
Okay.
you may go.
Okay,
Yeah.
sure. Yeah, thank you. Sure. Yeah, so hi everyone. So the topic of my talk today is data intelligence for smart buildings. So the talk will be centered around the usage of data and artificial intelligence, machine learning technologies for bringing about energy efficiency and sustainability in buildings. So yeah, there are multiple levers through which the energy efficiency can be brought about in commercial buildings. But for the agenda for this talk, we'll be touching upon a few use cases where we are using AI and ML as a technology enabler for bringing about energy savings in commercial buildings. Yeah, so to start off with, I'll just touch upon the first need for even using AI ML in buildings, right? So the infrastructure for AI ML comprises of everything from data collection up to data processing, storage, analysis, and also the feedback or the control. So to start with, if we have multiple sensors installed on different equipment in the building, and they are constantly collecting data, it becomes very important to collect this data on a real-time basis for us to be able to derive value from the usage of AI ML and providing insights in a timely fashion. So the streaming data is stored and processed and analyzed in a cloud platform. It could be a cloud, it could be even an on-premise server. So once the data is presentable for analysis in a certain format that can be consumed by AI/ML, it is then analyzed, and it is also visualized even before the analysis happens. It is visualized on a real-time basis in order to enable the automated real-time asset health monitoring. So this remote monitoring of the asset's health is very important, very valuable in the current pandemic context, right? So because remoteness is key, Yeah, previous slide, please. If you could go back to the previous slide. Yeah, thank you. Yeah, so we also use predictive maintenance, which is AI enabled, in order to answer 4 major questions. That is, why do we need predictive maintenance in place? First, in order to find out what is going wrong. Second, to find out where it is going wrong, meaning in which asset something is going wrong. Third, to find out why it is going wrong, or more like the root cause of what is going wrong. Fourth, what should we do? What action should we take in order to prevent that failure from happening? So this is the objective of predictive maintenance. And once we have these analytics insights, they are also validated by the subject matter experts or the technicians. And these insights, in the form of notifications and alerts or recommendations, are then passed on to the closed loop control system in order to take the automated control action. And for any AI ML system to be effective, it has to have a continuous learning. So that is why we have a continuous loop feedback for the AI ML system to learn continuously from the real-time data that is getting collected. So once this is operationalized, once this workflow gets operationalized, as and when there is data coming in, there are insights being generated. Yeah, to the next slide, please. Yeah, so there are many ways in which we can realize energy savings in commercial buildings. One of them is through energy baselining. Now, how machine learning helps here is by learning the energy consumption patterns in the past, in history, based on the environmental conditions, based on the weather patterns, the occupancy density, etc., in the building in the past. So once the machine learning model has learned these patterns, it is able to predict on a real-time basis, under these given conditions, this building of this size with this occupancy is expected to consume this amount of energy. And if the actual energy that is being consumed is much, much higher than the predicted value, we know that there is something wrong. So some equipment is consuming a lot of energy. So by breaking up the energy consumption patterns into different granular levels, we will be able to pinpoint and say that this particular equipment is the one which is the culprit. It is consuming more energy and it needs attention. And optimized environment control and ventilation is yet another way to achieve energy savings. So if we have a very effective ventilation strategy in place, for example, if we do the ventilation on a dynamic manner, instead of having a fixed ventilation strategy, if we do this dynamically, based on the weather patterns, based on the occupancy, based on the time of the day, how much fresh air should be brought into the building at what time, right? So we will need to bring in more and more fresh air when it is conducive. Otherwise, we'll be adding excessive load on the HVAC system. So water efficiency is yet another way. So apart from the power, there is also consumption of water and gas in any commercial building. So detecting leakages in terms of water efficiency and plugging these timely will also go a long way in bringing about energy efficiency. Ventilation and temperature control, also based on the air quality, is important because air quality, especially in the current pandemic context, has become imperative to maintain good air quality in the building. So if we are able to predict that the air quality will go bad in the next whatever number of hours, we can proactively take measures in order to improve the ventilation in the building and at the right time, meaning at the time that is economical to bring in fresh air. Next slide, please. Yeah, so in the context of data centers, a metric that is used to measure the energy efficiency is PUE, which stands for power usage effectiveness. So it is nothing but the ratio of the amount of power consumption by the IT equipment to the total power consumption in the data center. So in an ideal scenario, this PUE value is expected to be 1, meaning all the power that is consumed in a data center should be consumed only by the IT equipment. But in reality, that is never the case, because we also have cooling loads. We have HVAC equipment, CRA units, and chillers in the data centers as well, in addition to the IT equipment. But it is good to always minimize the amount of energy that is consumed by others other than the other equipment other than the IT equipment. So one major way to do this in a data center especially is through prediction of hotspots. So there is a high correlation between the power consumption and temperature. So if we are able to monitor the temperature effectively on a real-time basis, we will know that those zones where the temperature is going high is a hotspot, and there the power consumption will go high, definitely. So we can take proactive measures in order to change the load, distribute the load in such a manner that the energy consumption in those racks and servers comes down. Another way to achieve this in a data center is through equipment diagnostics. So there are multiple equipment which consume a lot of energy in a data center as well, like in any commercial building. The CRA units, the chillers, the DGs, all these, the health of all these assets or equipment in the data centers need to be monitored, need to be any risk or any fault with those equipment needs to be diagnosed at the right time. And this also will go a long way in energy conservation in data centers. And in order to prevent hotspots from happening, we have intelligent air management methods in place. Next slide, please. So in the hospitality sector, the most important aspect is occupant comfort. One major consumer of energy in the hospitality sector is lighting system. So managing the lighting system also dynamically, similar to the ventilation strategy, if we can make the lighting also variable by looking at the ambient conditions based on the occupancy density, and by changing the intensity and hue of the lighting system dynamically as per the load, the temperature, the amount of light that is available on a certain day, on a certain time of the day. So all these can contribute in energy savings in the hospitality sector. And yeah, energy consumption breakdown. Yes, we will need to break down the energy consumption to the most granular levels possible, to the meters and the sub-meter level and at the equipment level as well. Because if we don't know from where the energy consumption is going high, we will not be able to control it. So dynamic environment control also, more like the temperature control, also is another way to achieve energy savings. So for instance, consider a resort with multiple rooms in different regions of the building. So some rooms may need a very high set point, and some of them may not need, may need a much lower set point, in the sense that some rooms which are facing or are very close to some kind of vegetation may need a very low set point. So if we can do the set point adjustments also, we will end up saving energy. Next slide, please. Yeah. Yet another type of commercial buildings which consume a lot of energy. So one major consumer of energy in hospitals is the escalator, the lifts, right? So most of the patient flow and material movement in hospitals happens through escalators. And if we can optimize the patient flow dynamically, if we can optimize the material movement using queuing models a little smartly, and we will also end up saving a lot of energy. Yet another way to do this is by environment control. So temperature control in the context of hospitals. There is a lot of energy that is being consumed for the process of sterilization of medical devices. And for this process, it is very important to maintain the temperature in that very specific zone, in that specific range. And if the temperature goes beyond or below that specific limits, those specific limits, the process has to begin all over again from the very beginning. And this will end up in a lot of energy wastage. Hence, it is very important to monitor this and control this very effectively. Yeah, next slide. So in the manufacturing sector, the manufacturing process itself, the operational efficiency of the manufacturing process can be improved, and hence we can also save energy in turn. So DER scheduling and forecasting is one way. Now DER is distributed energy resources. If there are multiple resources or sources of energy from which a certain factory is, say, drawing power today. So it could be from the grid, it could be from various renewable energy sources. So they could have a rooftop unit, solar unit, or they could even have battery storage. So when do you draw how much amount of power from each of these sources? So optimizing this can also help in bringing about energy savings. And by optimizing the operations also, the workforce management, utilization of various machinery, utilization of the space in the factory can also help in energy savings. And process improvements and cycle time reduction, this is one important use case for AI in the manufacturing sector. So if there are redundancies in the manufacturing process, in the manufacturing cycle, or in the calibration cycle, these redundancies can be spotted automatically using data analysis, and this can help improve the process, in turn bring about energy conservation. Next slide, please. Yeah, so
Ms. Sandeep, just sorry that I interrupt again, but it's really, we are running out of time, so I appreciate your summaries. Thank you.
Sure, yeah, just 2 more slides. So in this context of smart cities, one important theme today is sustainability. So if we can plan the infrastructure using digital twins, now digital twins in turn leverage technologies like AI and immersive technologies like augmented reality and virtual reality, we can have a much better planning in order to save space and have the right kind of buildings constructed in the right spaces in the cities, which also will help in energy conservation. So waste management is yet another use case. So there are automated ways using computer vision in order to do waste management effectively. Specifically to spot if there is mixing of wet waste and non-recyclable waste that is happening, and take measures in order to prevent this from happening. And disaster management is yet another use case where we are able to predict using weather forecasts what is, for instance, what is the intensity at which a certain hurricane is moving, and be able to proactively tell those particular populations which will be affected. And also in the case of disaster management, be able to streamline the disaster relief efforts effectively in order to see that those areas which are affected maximum receive relief efforts at the earliest. Yeah, next slide, please. So yeah, in the space of smart mobility again, so AI is coming in handy for electric vehicles to predict the battery life, and also to enable fast charging of the batteries in electric vehicles, because these two are the pressing problems when it comes to EVs. And if we can also monitor the traffic and crowd on a real-time basis and schedule the transportation, the public transportation, and if we can analyze the data, the past data, and as per the seasons demand, we can schedule the fleet, and this will also help in fuel efficiency. In the case of shared mobility, route optimization for all the people who are sharing the ride in order to reach their destination in the minimum possible time is also being done using AI, and AI is being extensively used for this by Uber, Ola, etc. And yeah, so this definitely helps in bringing about energy efficiency in the context of smart cities. Yeah, that's all I had. Thank you.
Thank you, Ms. Sandeep, and for your presentation. I see that different sectors are mentioned in the presentation, integrated with the AI technologies, and how data intelligence also support these energy savings, actually. And these technologies may also be, in my opinion, utilized for flexibility to make the user understand when is the best time for using energy as well, of course. So thank you. Ve şimdi son konuşmacımız olan Sayın Onur Günduru'ya gelelim.
Now we will switch to our last speaker, Onur Günduru, who will discuss this smart city concept and support his view with certain practices. Energy and demand flexibility and energy integration will be his topics, and we'll try to associate the topic with actually certification efforts. The floor is yours, Mr. Onur. Thank you. I would like to share my screen now, my presentation. By the time, if you have any questions, please do write them into chat box as we are running out of time. Maybe we can address them for a couple of minutes. Thank you very much. Can you see my presentation now? Yes, we do. We can. Hi again. I would like to thank other speakers for their valuable presentations. Now I'll be talking about a complementary area, a short introduction. I've been working on energy efficiency for the past decade, as well as carbon reduction. I am a computer engineer, and we have been involved in different R&D and innovation efforts, and we are accelerating them. Breaker project was one of them, where we had a customer-facing demonstration, and we achieved actually good results. In the DREAM project, we focused on demand response energy analysis, focusing on energy distributions, and in Carbon Ninja, actually we focused on producers to decrease their energy-based carbon emissions. Actually, we are at every side of the table, and we also work in cooperation with various NGOs so that we can actually add momentum to carbon emission efforts. And we conduct demonstrations accordingly with our colleagues. Now, I will very briefly refer to the smarter buildings, but in order to have smarter buildings, we have to have the smart ones first. European Energy Performance Directive refers to voluntary or optional implementation. Instance, I will also refer to that, but let's look at what a smart building is. There was a short introduction of it already. The smartness of a building refers to its ability to sense, interpret, communicate, and actively respond, if necessary, in an efficient manner to changing conditions around it. Here, they may relate to the operation of technical building systems or the external environment, including energy grids, or the demands of the residents living inside a particular building. What are the advantages of a smart building? It, to start with, optimizes energy use, and it optimizes local energy storage. It predicts automatic diagnosis and maintenance, and it provides improved comforts, which is really crucial as we actually ensure energy efficiency and reduce emissions. We don't want to compromise on comfort or health. That's why all the researchers pay special attention to this area. As part of the legislation, the European Union referred to Smart Readiness Indicator as SRI, and here countries are expected to implement it themselves. I think certain items have been neglected for a while, but I think they will come back now with the relevant action plans. Here, this focuses on energy efficiency and overall in-use performance, adapt their operation to the needs of the occupant, and adapt to signals. Here, Smart Readiness Indicator refers to energy use, maintenance, comfort, easy use, and data collection, health of the building, and comfort, also energy flexibility. And here there are 7 sub-headings and 3 covered under 3 main headings, 3 main categories. I'm now going to skip these parts so that I am on time. Here on the energy operation and performance side, they have a 1/3 share score in the score. In order for the building to be completely smart, we need to ensure maximum amount of points. That's how we design and operate our systems. User needs also comprise 1/3 of this grading system, and answer or response to the needs of the grid represents 1/3 of the results. When we look at actually energy savings, we see that it's half of the operational side, comfort together with maintenance. And then we have comfort, convenience, information to occupants, well-being. So they actually have like 1/4 of contribution. But when you look at the last element, which is energy flexibility and storage, you have a huge score advantage. So having a smarter building means being responding to the grid, and then actually having an impact regarding the carbon emissions. Therefore, in actually Mediterranean, this has a shorter. We have a shorter period. That's why I wanted to highlight this part. So as for the other sections, they also matter separately, individually, but there were presentations on those components. That's why I will focus on the last side. So an example grading shows us that it has the energy demand flexibility has a 25% grade, which makes it well behind in terms of overall evaluation. Is it fair? I think it's fair. Because when you look at it in terms of carbon emissions, one of the sine qua non is that the building should ensure how it responds to this emission situation and in line with the building. So our emissions mostly result from energy consumption, mostly result from emissions. So we should be aware of it as soon as we plug in a device. We don't think about the rest, but there are systems, or we need systems that will help us think about beyond plugging in a device. So what is energy demand flexibility then? Let's briefly look at this. Shifting electricity consumption to coincide with times when electricity is clean and cheap means energy demand flexibility. And in our country and Europe, although there are countries a little ahead of the others, we see baby step. These systems can be way better. And the energy industry mostly gets balanced on the supply side. When there is surplus of energy in the grid, power plants can be actually deactivated. And when there is a gap, they are activated. And we know that we have very beautiful systems supported by AI, providing region-based predictions and creating baselines for consumers, or recognizing the source that generates electricity and making predictions are all great, and they have been addressed by the other speakers. But on the supply side, taking such relevant measures isn't enough, because when you do that, you will know that a renewable energy plant will not be able to generate more electricity. If you do not run the facility due to price reasons, then you will have to turn to fossil fuels and activate a natural gas plant. And you will then weather the climate change issue in a polluted way. And it's think of a summer day when everybody goes to their homes and turns on their ACs, activating natural gas energy plants and providing comfort at homes lead to a lot of carbon dioxide emissions. And that means actually consecutive steps contributing to excessive emissions. And here you need to actually plan these sites and even shift the times so that the power plants can be actually put a little aside and the consumer side is taken more into view and establish a connection between the two. There are certain scenarios that are quickly deployed. Professor Papadopoulos showed a few of them. I don't mean to reiterate those examples, but let me say that in order for the grid to respond to different load levels, for example, we need to overcome a peak and make sure that the consumption is quickly reduced. At this particular point, as we decrease consumption, the resources we use is actually different from the ones when we postpone consumption. Many resources should be integrated. For example, when you cut down on lighting, you cannot actually light the building more 1 hour later. You only make certain savings. But heat changes, for example, can be achieved by load shift in terms of heat management. Because, the thermal storage in a building resulting from conditioned air might help you have a cut down for 1 hour and then activate heating. And that wouldn't actually cause you to compromise on comfort. Only you will provide heating later. So lighting is another example than what I emphasize here. And here energy flexibility paves the way for renewable energy, and it has a key importance. It's one of the main items. Automatic management of these systems is another item here, and electrification is out there, and we see actually distributed consumer needs. It's becoming more and more difficult to predict them. And together with the development of renewable energy systems, we see fluctuations in supply. Solar power is becoming diminished, or wind may be actually passive, or there's this earthquake and geothermal generations actually increase due to changes. So there is this multifaceted dynamic regime, and you need automated systems. And actually, it should join the demand side. That's what I try to state. I already referred to the renewable energy, and I will skip this part. So what kind of practices do we see on the demand side flexibility mapping? In industrial, commercial, and residential units, we might have certain practices like power to heat, where you can have thermal storage. Here you prepare the heat beforehand and need it, and use it when needed. Or you can store hydrogen in commercial buildings and residents. You can have storage for electric vehicles, or you can consume from them, depending on the need of the grid. Yeah, you have a storage means, but you need to orchestrate it. We can talk about the smart appliances as well. There are very successful examples. For example, according to carbon emission data, home appliances work accordingly. For example, I tell my washing machine that it should operate when the carbon emission is low, but make sure that my laundry is washed when I come back. So it tries to wash it at the lowest emission time of the day. There are very good examples of it. We can also achieve this in industrial processes, and actually numerous processes need to be rearranged and made flexible according to these facts. When we come back to the building site, lead survey also pays attention to this aspect. There are 2 points. And here, one of the points is related to participation in demand side, in demand response to technologies. And another point is given when it actually participates in an existing demand response. Here we need to look at the critical loads and non-critical loads. Here we are dealing with non-critical actually loads in the system. When we include them in our programs, we reach the highest level of flexibility. Sorry to interrupt, dear speaker. Please wrap up your part in 1 minute. Of course, I'll do my best. In order for them to happen, we need to have an overview of an aggregator site. An aggregate as they lead to healthier data, more quality data, and that enable you to manage those flexible loads. Here we're talking about the industry professionals who provide actually information. We refer to security, and one of the most important items is cybersecurity. And here, actually, you can turn on and turn off devices and even make a grid collapse. That's why we should ensure resistance, security, and low carbon by actively addressing smart and smart devices integrated to the industrial aspects. That's why I kindly request all private sector representatives, academics, or freely recruited climate students to cooperate with me. We'll be happy to produce together. It's a multifaceted study. Thank you very much for your attention. If you have any questions, I'd like to address them now or after the session. Thank you very much, Mr. Onur. Especially smart grid indicators are important, and also you refer to the energy demand side, and calculating those indicators and integrating them to buildings hopefully is not a far future. We have only 2 minutes to wrap up this session. I'm checking whether there's any questions, but I cannot see any questions. I think we'll not be able to address them at all. I kindly request our audience to pose their questions to communicate with us. Mr. Altug says it's out there. Yes, maybe we can answer this question briefly. This is for Mr. Altug. As you know, TSS 125 standards are being revised, and we are reaching the end of it. That is just a comment. It's not a question, it's a remark. Okay, then let's end this session. If there are any questions, you can actually access our participants through email. Just to wrap up, I'd like to thank all the participants for their contributions. Digitalization, smart grids, and all other elements were explained in a very educational way. And we refer to buildings, and we hope that we're going to have those buildings with more renewable energy integration. And we follow up on the developments in the European Union. I also take part in smart city projects, and with the actually green deal, we're going to have actually bigger actions, and conferences like Zero Build will increase awareness. Actually, energy efficiency should also be discussed as part of the school curriculum like this. Thank you very much, everyone. Have a good day. Bye-bye.